Mm. Okay. Hi everyone. Welcome to today's session on introduction to quantum machine learning, and we have very special speaker with us today, and his name is Pablo. You can see his smile, really pretty. Um, and so who is Pablo, and why has he come to speak with us today? So Pablo is a theoretical physicist, and he currently works as a quantum algorithm scientist at Sandu. So, although he argues with me that it does more quantum algorithms in chemistry, he also has some papers on quantum machine learning, which I think it's really interesting and would really benefit each and every one of us today because everyone is talking about machine learning, but I think that there's sort of more to it. And there was this article by Geeks for Geeks saying perhaps it's the next big thing. So, I mean, there are a lot of debates. I don't think it's the next big thing, but I think it's something that we sort of want to look into. So, it's also going to help us debunk some myths and truths and misconceptions around um, would machine learnings be super fast, right? Would they be super efficient, right? Would we still have issues with um, localization and all those kind of things? So, before, so let me not take many more time. So, Pablo, welcome to the community. We're really
Thank you.
excited to have you today. And yeah, so if anyone has any questions, you can just like drop it in the chat. I would make sure he sees it. So you have the floor.
Okay, thank you so much, Bumi. Um, so as well, let me quickly introduce myself. I am, as Bumi has mentioned, a theoretical physicist. I also work as a quantum research scientist, and also, well, I'm mostly specialized in chemistry, in chemistry applications. So, um, although I know a bit of quantum machine learning, it's not my specialty, but I'm happy to answer all your questions. Okay. Uh, so let me first, since I want to make this a bit dynamic, I will be following some demos of how you can take your first steps in quantum machine learning, and for that I will share a screen and tell you first a bit about um, what are the two main yeah the two main the two main well libraries that one can use to program in quantum computing are Qiskit, which you can find here, and you can also program quantum computers in real time. And then there is Pennyline, which is also super great and the one that we will be using in this presentation. So to install Pennyline, you can click here and you will get pip install Pennyline, and you can also create your own account. So if you go to profile and you create a profile, you will be able to learn, for example, and follow the demos in your at your own path at your own pace. Okay, so what we will be doing today is just presenting what are the first things you can do in quantum machine learning, so to say, or in quantum computing more generally. And for that, we will start with a very basic tutorial. Okay, so what is quantum computing? In quantum computing, we will be playing around with qubits, which is the generalization of bits. So in bits, usually you have either zeros or ones. Qubits are a linear combination, for those more mathematically oriented, a linear combination of 0 and 1. So you can have 0 plus 1, or you can have 0 minus 1. And you can also, these coefficients you put in front of them have to be normalized, but they can be complex numbers. Okay. So what kind of operations we can do with these qubits? Well, what we can do is we can rotate them. So rotations will be the basic gate that we will be applying to qubits. So for example, a quantum circuit will start with a qubit, for example, starting in state 0. We represent it with this notation, 0. And then we will apply different kind of rotations. So we will have uh, an X rotation with some angle. The x rotation is represented with this matrix, and then rotation y, which is a different matrix, but again it has angles, and you can see they resemble each other, but they are slightly different. And finally, once we have done these two rotations, we will measure the expectation value of a third matrix, which will be this one, which is called the Pauli set operator. So overall, mathematically, what we will be doing is this operation over here, uh, which well, which you can get by so this thing here is the same as you're getting here, and then you put the set C in the middle and the conjugate of the state, and you put this all together and you obtain this thing. Okay, so let's do it on our own laptop. Okay, so we start once you have installed Pennyline, as I mentioned here. You create your own Conda environment or whatever, and you do pip install. So we will import Pennyline as QML, I guess that from quantum machine learning, and we will also import NumPy from JAX, so the JAX version of NumPy and JAX itself. And Pennyline, the first thing it does is it creates a device. What is a device? A device is something that you will use to measure. Well, you will measure something in the end, or you will take such or expectation values or something like that. So it's an object that you will use to measure the result of the circuit. And then you also, so for example, this thing, this is the type of device that we are creating, and the wires is the number of qubits that will appear in our circuit. And then you also have to create the circuit, and the circuit will specify what are the gates that you will be applying. Okay. So I have coded them up here. So this is, for example, here. Sorry. So let us follow. So I import Pennyline as QML, and then JAX, and I guess this is not needed really. Then I create the Pennyline device, and I will be creating the circuit, and I will use this decorator as a way to tell the system that the device is being used in this circuit. Okay, so for example, if we put as these two angles to the circuit, the angles to the X and Y gate, we can measure the expectation value, the set expectation value of this circuit, and we will be getting this number. Okay, so the nice thing about Pennyline, so this is a very simple thing I just explained, which is up to here. But the nice thing about Pennyline is that it's fully differentiable, which means that you will be able to use JAX or other libraries to take gradients throughout the circuit, which is something that you're probably very familiar from machine learning. And so we are going to use JAX grad to take the circuit with respect to the argument 0. The argument 0 in this case is the matrix of the angles, so it's both at the same time. So if I do this, I get the two gradients with respect to the two angles. Alternatively, if you find this slightly confusing, you can also define two parameters separately that you pass to the circuit, and then you can define the angles, and you can also run the circuit. Again, this is the result, the same as we obtained here, and we can also take the gradients computed. Oops, sorry. What did I do? Oh, probably wait. Let's copy so it's faster. So if we do this and we substitute like this, it should work now. Okay, and now we get the two the two angles. So, okay, that's all fine. But in machine learning, we often want to um, define a cost function and optimize the result, right? Because we have this circuit over here, and we want to do something more fun. So let's try to do something. Let's try to figure out how these angles need to be in order to maximize or minimize the expectation value uh, that we are measuring in the end. So we will define a cost function, which will be the value of the circuit, okay? And now we will start from two random states. You can put it whatever here. We can repeat it afterwards if you want. Say two values for the angles, and we can. So initially, the value of the expectation value is almost 1. Let's try to minimize it. Let's try to make it as small as possible. So if you're familiar with JAX, the idea is we will optimize. We will take the JAX optimization library, and we will pick gradient descent, the function cost, the step size, and then with no acceleration, and we will take 50 steps with initial parameters being the ones we defined here. And let's see what happens. So if we do this, you can see that it starts near 1, as we mentioned, as here, but then the gradients pick it up and quickly go up to -1. So they are minimizing the cost. So this is what this demo is about. Now you know that you can use gradients, and well, you can use gradients to minimize or maximize, doesn't matter, the some expectation value or some observable of a quantum circuit. Okay, so this is a bit different from what you've seen usually in machine learning. In machine learning, you are not working with these complex matrices, but in general, this is what we will have in quantum computing. So in quantum computing, we will have unitary matrices all the way around, and we will have measurements in the end. Is there perhaps it's a good time to have or to ask questions if you have any, and or if not, we can jump to the next demo I have prepared.
Okay. There are no questions yet, so you can just continue.
Okay. Okay. So the next thing I wanted to discuss is, okay, we have discussed how to take gradients using JAX, but this is obviously a simulation, right? So here we are using a simulation. In a quantum computer, we don't really have JAX. Why we don't have JAX? Well, all these calculations are done in a classical computer, so you're not going to be using JAX directly in the quantum computer. So you have to figure out how you're going to compute gradients there. And really, uh, it's not an easy question or an easy way of solving things, because usually the problem with quantum computers is that we don't have direct access to the state of the system, which means that if you give me a state, a quantum state, this quantum state will be a superposition. But the problem is that if you measure it, if you measure this superposition, the superposition will collapse to one of the basis states. The basis states are either 0 or 1. So if you have 0 plus 1, when you measure, you will only measure 0 or you will measure 1 with equal probability, but you won't measure the superposition itself. Therefore, measuring gradients is not as easy as in classical computing, because in classical computing, you can read a state and it doesn't matter, it doesn't affect the computation. But if you read a quantum state, it really collapses the state and you no longer have the state available for the rest of the calculation. So let's think about how you would compute the gradients. Well, in order to compute the gradient, what we will have to do is we will have to measure an observable. An observable is something that you measure from the circuit, and this means that you will have to run the circuit a few times. Specifically, if you have an observable B here, anything that you measure at the end of the circuit, and this use being the circuit that you apply, this quantum circuit, usually the way you measure the final expectation value is something like this. So, for example, if we go back to the previous uh, previous demo, U would be the combination of Rx and Ry, and B would be this sigma set, the Pauli observable, which, by the way, is this matrix over here. So this is B in our case. So in order to measure the gradient, mathematically you can compute it with this form. So you have to compute the expectation value of B with the parameter shifted. That's why it will be called the parameter shift rule, by plus pi halves and then minus pi halves. And you will have to subtract these two expectation values and normalize the result. And that will give you the overall expectation value of the gradient of the circuit. Now, the thing is, you will have to run this many times in order to get an expectation value, because expectation values are something that you sample. And you will have to do it for each gradient that you want to measure. So let's code it again. Let's do the same. So you start with importing again penny lane and JAX and matplotlib, because we will plot things afterwards. And also we will input these configurations to JAX and create a random key. As we discussed previously, we will also create a device. And in this case, it will have 3 wires, okay? And the device will be a default qubit. Before it was Lightning qubit. There are a few devices. You can check them up in Penny. Lightning is optimized for speed, but we will take the basic version here, the default qubit. And this circuit will have an Rx gate, an Ry gate, and an R set gate. These are rotations according to different axes in a sphere, in each of the different qubits. Then there will be a ring of control NOT gates. These are the same as the classical control NOT gates, which will go from 0 to 1, from 1 to 2, and from 2 to 0 again. And then we will repeat the pattern with the result of having a circuit that looks like this. So you have Rx, Ry, Rz, then the C notes, and then again the gates and the C notes, and some measurement at the end, which is defined here. So this is the expectation value of Pauli Y and Pauli Z on their respective qubits. So let's do it. And also you have to define the parameters, and you will be able to plot the circuit. Okay, so if we go here now, so let's start importing things, and then we will define the circuit. We will run the parameters and draw the circuit. Okay, so here we have the circuit as promised. So now we will define the parameter shift rule. The idea of the parameter shift is that we will compute the result shifted by MP halves, by pi halves, and then by minus pi halves, and we will subtract them and multiply by 0.5, which is what we specified here. So, we can compute then the gradient with respect to one parameter indicated here, the ith parameter, okay, which will result in whatever, and we can apply it throughout all of the parameters in the system, resulting in this. So let's code it up. So we define the parameter shift as indicated, and now we can, for example, compute the gradient with respect to the first parameter, and we can also use it for the parameters throughout the circuit, for all the parameters that appear here, which are all these 6 parameters that we are inputting into the circuit. Okay. So now, if we have these, we can also alternatively compute the gradient of the circuit using grad, and we compute it like this, and you can see that this number, since this is the first parameter, checks out to be the same as this one computed with the parameter shift rule. Okay. Obviously, if you now compute, there is a handy function already encoded, which is called param shift, which will do the same as we manually did here, and will return the same results. You can check that this thing is the same as this one. Okay, so let's try to do something. I have presented two ways of computing the gradients. One is with auto differentiation, or taking the gradients of the circuit as if it were a JAX code or something, and the other is with the parameter shift rule. But they have a key difference. When you do when you use auto differentiation, you don't have to run the circuit every time for the different parameters throughout the circuit. But when you do the parameter shift rule, you have to do it. The problem is that this second one will be the only one available when we are running a quantum circuit in real hardware. So what we can do is we are going to benchmark them. We are going to benchmark what is the cost. So again, here we are defining the differentiation mode with the parameter shift rule, and defining the same circuit as before. It's just a different, or is it? No, sorry, this is not the same. This is not the same circuit. This is a different one. But the key thing is that we are going to use the parameter shift rule to compute the gradients. So you can see that we have 4 qubits. The parameter size, so the number of parameters, is 180, and the result when randomly initialized is this number over here. Okay, so let's try to compute how long does it take to compute the forward pass. So just one expectation value. So it takes a bit, and it's almost 0.1 second per loop. Now the gradient will be slightly longer, I'm afraid, and it will take 5 seconds per loop. We can run it like this, and I will leave it here for a second. If we are doing back propagation, which is the opposite, as I mentioned, not the opposite, but the alternative way, we can input here back propagation now, and we will get the same result, except that now the forward pass will again be very similar. The cost of will be very similar as before, but the gradient, taking the gradients throughout the circuit, will now be much faster. So here, it will be back in a second. Sorry. It took around 5 seconds per loop. Now it will take only 1 second. So it will be significantly faster to compute the gradients instead of using the parameter shift rule. Let's see. Okay. So let's now try to do a benchmark in the sense of do a formal time comparison between the two options. I will not run these layers, these cells, because they are a bit expensive, but I have already run them. You can see them here. The thing is that if we compare the forward propagation with the backward propagation, you will see that the parameter shift rule really scales much worse than the back propagation, because back propagation uses the fact that you can read states to memory in order to save computation. So it's trading some computation by memory, which we don't really have in quantum computers, as I just mentioned. Has it finished yet? I'm not sure. It hasn't. I'm not sure why. Okay. Let's leave it here. Is there any question now, Bumi?
None yet. None yet.
Okay. So finally, so I had prepared three demos for this for this presentation. We've already seen the first one, which is basic tutorial of how you can implement a circuit and how you can take gradients and so on. Then I have discussed the different ways of computing gradients with backpropagation and also with the parameter shift rule. The parameter shift rule being the one that you will be able to implement in real hardware, in physical hardware, physical quantum hardware. And finally, I wanted to explain one possible application of computing gradients in quantum circuits, particular in chemistry, so VQE. So what is VQE? VQE stands for Variational Quantum Eigensolver. So what this thing is doing? So variational because it will vary the parameters of the quantum circuit, quantum because of quantum, and eigensolver because it will be computing the eigenvalues of a Hamiltonian, and the eigenvalues being the energies of a system. So what this circuit will do is it will try to estimate the energies of a Hamiltonian that we will be inputting. So how we do this? Well, we start as before, importing jacks and blah, blah, blah. Some symbols, these symbols will represent the atoms that we will be using. We will also indicate the coordinates. So for example, this means that there will be a hydrogen in these coordinates and then another hydrogen in the other two. And we will be able to create a Hamiltonian with those symbols and coordinates. So if we go again to our, did it finish? Yeah. So you see 5 seconds, as I mentioned before. Sorry. Okay. So yeah, so we start by defining the symbols and coordinates. We also define the Hamiltonian. You can see that we will have 4 qubits because this will be a minimal basis set. And then the Hamiltonian will be something like this. So it's pretty lengthy actually. But let me give you a quick insight of how this looks like. So this is the identity. So sometimes the identity is the identity matrix 1 1 in the diagonal, and the rest is 0. So you will have this term, then you will have a set gate, set being the Pauli set gate on the first qubit too. Then there will be another set in the second qubit. Then now something interesting, there will be some terms that are the multiplication of two different Pauli gates. So in this case, the 0 qubit and the second qubit. And you will see that there will be not only set gates, but if you move a bit around, you will also see X gates and Y gates. So this is the Pauli string representation of the Hamiltonian in a minimal basis. Now, okay, so that's all fine, a bit complex, I guess. Let's try to code up the VQE, the variational quantum eigensolver, and let's try to see if it works. So we are going to define a device as before. The device tells you what are the measurements or how you're going to measure things in the end. So in this case, it's the Lightning qubit version, which is the performant version of the device. We will have to say how many electrons we have. 2 electrons in this case, because we have 2 hydrogen atoms here. So each hydrogen atom will provide 1 electron. And we will define a Hartree-Fock state with those electrons and those qubits. So what is a Hartree-Fock state? A Hartree-Fock state will be a state that is a basis state. So it will be a state that you can represent like this, 1 1 0 0 in the 4 qubits. So it won't be a superposition. It will be just one of the basis states. Now, why is this Hartree-Fock state interesting? Well, it will usually be the basis state that is the closest to the lowest energy state of the system. The lowest energy state of the system is usually a superposition, but you have to start from somewhere, and there are many superpositions that you may come up with, including, for example, 1 1 plus 0 0, which is an entangled superposition. So what we will be doing now is we will start from the Hartree-Fock state, and we will try to minimize the state of the system. So we will tune the state of the system in order to minimize the energy. This is what the variational eigensolver does. So what will be the circuit? The circuit will be, uh, we will have a base state, which will tell us how to prepare this Hartree-Fock state. In this case, it will be just two X gates, two NOT gates in the first and in the 0 and 1 qubits. And then we will have some parameters according to which we will implement excitation of the electrons in the lower qubits to the higher qubit orbitals. And finally, we will measure the expectation value of the of the uh, of the Hamiltonian that we have here. And with this expectation value will tell us the energy, because the Hamiltonian has the property that when you measure the expectation value, you get one of the energies of the system. So this is a circuit. Now we will define again a cost function. In this case, it will be the circuit itself with the parameters that we provided. And we will pick the optax, which is a JAX optimization library, maximum number of iteration, convergence, tolerance, and we will be use stochastic gradient descent as the optimizer. We will start with the parameters being 0. Why? Because we are starting from the Hartree-Fock state, so we will just say, well, you're starting from the Hartree-Fock state. Tell me how should I tune my excitations in order to achieve the minimal energy state? The energy will be the cost function of this angle theta that I mentioned, and we will run the maximum iterations. For that, we will compute the gradients and optimize the state. This is usual. If you're familiar with JAX, this is the usual JAX workflow that we will be also using here. Convergence tell us whether the energies of the previous iteration is the same as the one in the current iteration. So if you run this, it's pretty fast, and you can see that we start from an energy that is not bad. It's minus 1.127 Hartrees. Hartrees is a energy measure, and we will achieve minus 1.136. So we have decreased the energy of the system throughout the steps. So can we plot it? No? So if we plot the energies according to the iterations, we will see that as we proceed throughout the optimization cycle, we are minimizing the energy of the system until it basically achieves what is the full CI energy, which is the exact energy. In this case, the system is very small, so we can brute force compute the minimum energy of the system. But usually this is meant to, or this procedure is meant to be useful when you don't have access to this full CI energy. And this is the value of the theta parameter. And you can see that it converges up to approximately 0.2, which should be 0.289 here. Okay. And that is the presentation I had prepared. Now, if you want, sorry, this is the kind of rotations that we are implementing. So we are implementing a rotation that excites the two electrons from the lower orbitals to the upper one. And this is what we have. Okay. So what should we do now? Bumi, should we answer some questions perhaps? Even the ones that you received before TAN? Or, yeah. Let me mention, so if you're interested in these topics, Pennyline has a ton of ways to learn. There are many demos you can see here, starting from very basic ones. So like this, then you have optimization, you have quantum machine learning, quantum chemistry. There are different devices. For example, you can run these circuits in IBM's quantum computers or in different other quantum computers, and even we have devices for high performance simulations. For example, AWS here. And there's a ton of things, I don't know. there is also many algorithms that you may be interested in. A code book. Well, there are many learning options. Okay, okay. So that was what I wanted to present.
Okay. Thank you so much for presentation. I think it's it's been a lot, and for those who are probably not, I don't know, too familiar with mathematics, you're like, ugh, what's this? Sorry.
Well, it's linear
Um,
algebra, fortunately. So it's not too bad. But yeah.
yeah, I actually agree. It's not too bad, and I think for those of you who also have background in machine learning, you've seen things like back propagation, you've seen things like gradient descent and things like that. I think it's just sort of showing you how you can sort of move these terms from what you're familiar with in machine learning to quantum, right? I don't know. I think I'm actually excited to like actually code
Mhm.
this out, and I actually want to do that.
Let
I'm
me
trying to see. Okay, yeah.
let me say before that. So usually people talk a lot about quantum machine learning, but it's worth mentioning that often the most promising applications of quantum computer are not so much in machine learning or AI. It's unlikely that we will be able to achieve the scale that will provide any advantage in machine learning itself. Mostly because machine learning doesn't have structure, but the applications where quantum computer may really shine are chemistry, things related to molecules or materials or these sort of things. And I mean, because electrons are quantum mechanical, so usually it's much more natural and much more efficient to simulate them in a quantum computer, or at least there are some advantages in simulating them with accuracy. And also in cryptography, also because in cryptography you have structure that you can sometimes exploit for your advantage. But in machine learning, it's a bit trickier, let's say.
Interesting. 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 So maybe we're not gonna have this super quantum ML thing in the future, but then it's really worth looking into.
Okay, okay.
Yeah. Maybe we can take the questions that we had like before the session.
Yeah, sure, of course. Do you want to read them or?
Sorry. Yeah, let me read them. Okay, so someone is saying, how do I combine machine learning and quantum computing as a beginner, starting out in machine learning and AI field?
Sure. So um, I think they share the same mathematical backbone in the sense that it's all linear algebra at some point. That there are some differences because in machine learning you don't have to work with unitary operations. Unitary means that they are reversible, so they are rotations in a high dimensional space. In machine learning, no, in machine learning they are not unitary gates, but here they are. But although they are similar in the mathematical aspect, they uh, they are also a bit different. So in the sense of their applications are a bit different. I would say, as I mentioned, that quantum computer is mostly oriented towards chemistry or towards material science, and machine learning has wider applications in other fields. Um, but if you're I mean, the good news is that if you're a beginner, there are a ton of resources online where you can learn pretty quickly and hands-on, such as the ones I shared. And it's well, at least for quantum computing I shared. And yeah, it's actually relatively easy. There is also a community of people where you may ask questions. I don't know. It's pretty fun, I would say. There are hackathons from time to time. So I guess that's the way to learn. Um, Combining, I'm not that sure, honestly. But so yeah. Um, let's see. Should I perhaps read the next question? there is another question. So, okay, there is another question called: in how many years you think we could have fully understood quantum computing? Well, I would say so the quantum the quantum algorithm, it depends on what you mean. So quantum computing is a very clear set of rules. So we know what are the rules that form quantum uh, quantum mechanics. Now, the field of quantum algorithmics and quantum machine learning are much newer. That they only have like 25 or 30 years now. So there is not much work done yet, but we are starting to have a clear picture of what are the main algorithmic tricks that you can do. Uh, there is obviously a ton of things of how to optimize things, and also in complexity theory, there are a ton of things that we don't know for sure. Although I'm not an expert in those fields, but yeah. So if you want to, so the good news is that it's a relatively new field, so it's not that hard to achieve the edge. It's similar, I guess, to in machine learning. So in machine learning, there are many things that are happening, but the basic techniques are already known and they are being exploited. And something similar happens in quantum computing. Um, so another question, I guess. So career opportunities for quantum machine learning, well, I guess that at this point it's still a very nascent field, and in the sense that most of the work is in research, I would say. And for this research, again, I would emphasize you have to enjoy doing chemistry, because this is the field where you will most likely be applying quantum algorithms. So think of quantum computing as high performance computing for chemistry applications and for material science application. This is the correct, or the most common way that you will be seeing yourself if you work in this field. Uh, However, for learning, there are a ton of resources. As I mentioned, there are two main libraries that you may want to be aware of. First is Qiskit by IBM, and then there is Pennylane by Xanadu, where I work actually. So this is a small conflict of interest, but my opinions are mine, uh, not necessarily my employer. Um, but there are many resources, and there are many communities, and you may definitely be able to learn if you are interested. And there are hackathons. It's a lot of fun, I would say. Okay. Then, are there PhD opportunities in quantum computing for someone with a master's in data science? I would say yes. So as I mentioned before, quantum computing is not such a complex field. Uh, However, I would say you must be comfortable if you want to do a PhD in quantum algorithmics. You probably have to be comfortable reading theorems and proving theorems and doing mathematics, because the problem is that at this point we still don't have uh, powerful quantum computers. We only have prototypes, so most of your work would be theoretical in nature, unless you're the one building the devices themselves. So if since this is a theoretical work, this means that sometimes and oftentimes you will be proving theorems about algorithms that we can't really implement yet. So you have to be familiar with that. But if that's the case, it's often not that hard to achieve the knowledge you need in order um, to perform well and to prove things and discover new algorithmic tricks in order to optimize the ones we have, or new algorithms altogether. And yeah, I think that's probably it. I'm not sure if there are any other questions. Okay, I think there aren't. So let me ask Bumi. Let's see. Okay, okay. So I think that's probably it. Unless if there are some other questions, I'm happy to. Oh, there are a few questions here in the chat. Sorry. Can you recommend any resources where one can learn as a complete novice? Yes, as I mentioned, uh, Pennylane.ai. I'm not sure if I can share it here. Perhaps not. Okay. So Pennylane.ai is a amazing web page where you have a ton of resources to learn, including demos. I showed you three of them. Then there is a code book where you have a more formal or structured learning uh, demos, let's say, or notebooks. You will learn step by step all you need to learn about the basics of quantum computing. Uh, then there are challenges and there are some hackathons around the world also from Qiskit and from Pennyline. Okay, so that's it. I'm not sure if there is any other question. I would say that's it. Mhm. Okay, so I think I will jump off. We can leave it here. If there is any other question for me, you can contact me, I guess. Thank you so much. Bye.